Hi, my name is Caroline Ninier. I'm an assistant professor at the University of British Columbia. And today I'll be talking to you about some work that I did mostly in my postdoctoral studies with Sid Sen at Microsoft Research New York City, along with our collaborators Giovanna and Shuvendu from Microsoft Research Redmond. So in this work, we're looking at improving the performance of search-based test suite generation. So what exactly is that? The goal in search-based test suite generation is to generate a set of test cases, aka a test suite, that explores interesting behaviors in the program under test. And usually the way these algorithms work is that they start by generating a test case population randomly, say by taking a random sequence of functions from the program under test and calling them with random arguments. And then these test cases are evolved through time by mutating them slightly, maybe adding a new function call to the test, or maybe mutating some of the arguments slightly. And then those evolved test cases will be evaluated on the program under test, and we'll collect some fitness feedback, usually related to program coverage. And if we find that, say, some test cases actually increase the coverage of the program overall, we will save them to that test case population. And we continue this loop, evolving the test cases, mutating them, saving the better test cases that increase coverage, either until we reach full coverage of the program under test, or we reach a certain time limit or other stopping criteria. So that's the high-level view. Let me show you how this works on a concrete example. Say the program we want to test is this Plateaus module where the main function that we're testing is this bump version function. And this is bump version is a Python function that essentially exists to bump version strings. So for instance, if you want to bump the version string 0.0.0, the default behavior is to bump the patch position. So going from 0.00 to 0.01. But there are a bunch of different arguments to this function. It does a bunch of different things. It can augment the version at different positions in the version string, can add some pre-release arguments, whatever. Okay, so lots of different if statements and different behaviors of this function. So say we want to generate a test suite for it via search-based test suite generation. We'll start by generating a few random test cases in our test case population. Here are some. Unfortunately, these test cases are not great in the sense that they don't actually call the function with a valid version string. And so an exception is thrown in that first helper function call. And so we get very little coverage of the module under test. And these tests are really not helpful to us. But that's okay, because the whole point is that we're going to mutate these tests and that over time, the tests are going to improve and cover more functionality in our program under test. So let's do that. Let's mutate the tests. Say we can update this primitive value to add a bunch of U's at the end, or perhaps we can add a new function call, and maybe that will also change the behavior of the test. Unfortunately, in both these cases, neither of these mutations are actually able to increase coverage, in that they are still calling bump version with an invalid version string, and we are still getting an exception in this first helper function. So we don't update the population. And unfortunately, in this case, even if we kept doing these mutations over and over again, we would not be able to increase coverage, because the likelihood via mutating this original population of getting a valid version string is very, very low. And so the search is stalled, and we could keep doing these mutations for several minutes, but we wouldn't get improvements. So what do we do now? Answering that question, what do we do now, is exactly what we do in CodaMOSA. So I'll talk to you about CodaMOSA, our core approach. Then I'll give you some highlights from the evaluation. For more, you can go see the paper. And I'll also touch on some remaining challenges for future research or improvement in this field. So the core approach of CodaMOSA. Let's return to our nice example where we were trying to test this bump version function, which is provided by this module under test. And we are unfortunately unable to ever update the population because our mutated test cases never actually produce valid version strings. So the first thing we're going to do in CodaMOSA is add an if statement. So we're going to add an if statement to check whether the coverage has stalled. And to do that, we're going to have to evaluate whether the coverage is stalled. And what we decided to do was just say that if we've gone through n iterations of this loop without ever increasing the coverage, we're probably stuck. Probably mutation is unlikely to get us anywhere. I arbitrarily chose n equals 25 as the n iterations, but that may not be the optimal value, but it is a consistent and not overly tuned one. Anyway, regardless, so the first thing in CodaMOSA is to add this check for whether coverage is stalled. And now that we have this check, we're actually going to do something with it, which is if we're in a case where we find that indeed coverage is stalled, mutation is not getting us anywhere, rather than continue to do mutations, we're going to ask for a hint. And we're going to, in particular, ask for a hint in the form of a test case for a poorly covered function in our module under test. The idea, right, is that if we can have a test case for a function in the module under test, hopefully that test case might actually exercise the function in a more expected way. And if we're closer to the expected functioning of that function, then maybe our mutations will get us somewhere. But it's not trivial. How do we generate an expected test in the first place, right? It's not trivial, but when we started working on CodaMOSA, there had recently been released this large language model named Codex. And Codex is a large language model that was released in August 2021 and trained on a whole bunch of code. And in the demo for Codex, these folks from OpenAI showed us that you could use Codex to, say, code up a JavaScript game. And so it seemed to us that if you could ask Codex to generate code for a JavaScript game, perhaps we could also ask it to generate some small example tests in order to get our search-based test suite generation unstuck. So that's what we do in CodaMOSA. When we get to this point where our coverage is stalled, we ask Codex to generate a test for the function that is undercovered. In this case, we might ask Codex to generate a test for bump version, and it would give us this test, for instance, is one of the ones it gives us. And then we do some work because Codex can essentially output arbitrary Python code, we do some work to extract only the core functionality out of that test case that is compatible with our search-based software testing framework. And we turn that test case into the correct format. We evaluate it on the test program. And in this case, actually, this test case greatly increases coverage of our test program. It exercises most of the lines in the bump version function. And as you can imagine, there's a whole bunch more code in this module under test, which I haven't shown you. But for instance, there's also this helper function, build version bump position. And we've also finally covered any of it, which we had been unable to cover before because we were erroring out at the first line of bump version. So this is clearly a useful test case. So we save it to the test case population. And now, because we have improved coverage in the last iteration, we can actually return to our mutational path rather than the Codex hinting path. And what we can do is we can take our good test case and we will mutate it slightly using our good mutational search operations. So for instance, we might take that test case and mutate the integer value 1 to -1. Or we might do a bunch of other mutations, but one of the other mutations we might do is mutate the integer value 1 to -2687. And then we evaluate these mutated test cases on the program under test. And we would find that that first mutant from 1 to -1 actually exercises this code of handling, essentially allowing negative indexing for the position. And the second mutant actually exercises this error handling case where we make sure to error out with a sensible message when an invalid position argument is passed. So both of these actually still increase the coverage of the program under test, and so we save them to the test case population. And just to give you a spoiler here of the evaluation, for the results on this benchmark, we saw that overall, the search-based software testing only approach was only able to achieve 18% coverage on this benchmark. The Codex only approach was able to achieve 65% coverage on this benchmark. But our approach was able to achieve, on average, 92% coverage on this benchmark. And if you want to do some math quickly in your head, you might notice that 92 is actually greater than 18 plus 65. And that is that our approach is really performing better than the sum of its parts, right? That this synergy between the generation of codex test cases plus the mutational search is unlocking behavior that is unable to be consistently found with both approaches individually. So that's the high-level view of CodaMOSA. Hopefully that makes some sense. There are some complexities here, which I have not touched on and will not touch on in this talk, such as when do we ask for a hint, how do we ask for a hint, and how do we handle the potential arbitrary output from codex. And actually, this last point is where a lot of the engineering challenges came up in this work. Solutions are discussed further in the paper, our ICSE 2023 publication. Just to give you a tiny bit of an idea, when to ask for a hint beyond that coverage stall, we also add some back off in case codex is really not helpful to us at all. How to ask for a hint, I'll show you an example of this later. It's just a very, very simple prompt with the implementation and a function header. And to handle arbitrary output, one of the significant things we did here was adding support for importing new functions that are called by codex or arbitrary syntax generated by codex if it increases the coverage of the program under test. All right, so that brings me to talking about the evaluation highlights. And before I give you the highlights, how was this all evaluated? I automatically extracted 486 modules from 27 Python projects. Those projects were chosen both from the evaluation of Penguin as well as from the Bugs in Pi benchmark. I ran each technique 16 times for 600 seconds each. I compared to two main baselines, MOSA, which is search-based software testing only, no codex hints, and codex only, which is essentially just calling codex the whole time without doing any mutative search. And in the paper, I'll evaluate a lot of the different design decisions, but I'll only touch on one of those in the challenges here. But you can refer to the paper for more details on the design decisions and how they affect our performance. But I'll just give you the high-level coverage comparison in the end, where we measure coverage of each techniques at the end of search times. I took the average overall runs, and I'll talk about statistical significance. By that, I mean I've used a Mann-Whitney U-test to compare the two sets of observations. So what we see here on the y-axis is CodaMOSA's average coverage on a baseline, on a benchmark. Each point or cross or plus is a benchmark. And on the x-axis is the baseline's average coverage on that benchmark. So essentially, if a point is above the x equals y line, that means that CodaMOSA has average higher coverage than the baseline. And what we see here is the x's are cases where the baseline had significantly higher coverage than CodaMOSA using the Mann-Whitney U-test. The circles are cases where there was no statistically significant differences, and the crosses are ones where we had significantly higher coverage than the baselines. And you can see that there are a lot more crosses than X's on our evaluation set. But actually, it's interesting, the distribution of the crosses is a bit different compared to the different baselines. So for instance, on the MOSA baseline, so that's the search-based software testing only, we kind of see like larger increases in coverage, meaning that, you know, maybe the test cases that are unlocked by codex help us achieve much higher coverage because they're unlocking new behavior. But actually, we have more consistent and more increases on more baselines compared to the codex only approach, so the one that doesn't have any mutative search. So what this means is that the mutative search is still really important in being able to exercise like little different behaviors in a consistent manner compared to codex only. So overall outperforming on these baselines. There's another part of the evaluation I wanted to brief. So first we'll look at the common causes for improvements. So I manually analyzed 20 benchmarks with the biggest coverage increases. And if you've done any work on search-based software testing or fuzz testing, it might not surprise you that for 15 out of 20 benchmarks, the improvements came from the generation of special strings. So our version strings or maybe say generating correct dictionary keys for a Python dictionary, or maybe say generating some valid JSON for a JSON parser, for instance. On 7 out of 20 benchmarks, Codex was able to construct argument data correctly without type hints. So Python is a language that doesn't have types by default. So if we're just randomly generating arguments and guessing the types of the arguments, we'll be wrong. Codex was right more often than the random generation was. And on 5 out of 20 benchmarks, Codex actually introduced new syntactical constructs that were key to exercise different parts of the module under test. So in this case, the join each function actually returns an iterator, I believe. And so this list construct, which is a built-in function, not an ordinary function that we would call in the search-based software testing, that list construct actually iterates over its argument. So it actually allows us to exercise the iterative elements of the program under test. And there are other things here like less than or equal to syntax, which was necessary to test some of the benchmarks. So that's the common causes for improvements. I also look at common causes for not improvements in the paper. And the other thing I wanted to touch on is just this question about whether Codex is copying tests. And the answer is, well, like sometimes, because here's one example. This is an example where there was high similarity, where I'm measuring similarity as normalized edit distance. Here's a Codex generated test. And here's a function in another part of the code base that we were testing, but which was outside of the prompt we sent to Codex. And if you look at these, you'll notice that the data that is passed to the functions is extremely similar. So it seems unlikely that Codex has generated this thing without having any idea of this other function, right? But let's look at this a little more systematically. So what I did is for all the Codex generations, I took their maximum similarity compared to some function in the code base outside of the prompt. So for this example, the max similarity is 0.7. And then I plotted that per benchmark. So here what we see is the y-axis is the cumulative percent of test cases with maximum similarity less than the x-axis. And each line is for each project. And so from the last example, we had similarity 0.7. You can see that most of these lines have similarity much less than 0.7. So most generated test cases have similarity less than that. In fact, most tests have similarity less than 0.4, right? So we have not too many of the Codex test cases are too similar to unseen tests, but it's definitely still a threat to consider when considering the generalization of this approach. So those are the main highlights from the evaluation, and I just want to close on some challenges. So where could we improve? One of the clear places to improve is on prompt engineering. The prompts we did here were super simple, kind of the most naive thing I could think of, just the implementation of the program under test, plus this prompt for a unit test for function x, where x is, of course, filled in with the function name. Similarly for methods and constructors and so on. And in the evaluation, we did an ablation study where we compared that approach to an approach that was just a little more sophisticated, where it added an example test in between the implementation and this prompt. And that was actually the ablation where we saw kind of the most sometimes improved performance. So even though regular CodaMOSA with this simple prompt was better on more benchmarks, we did see some large coverage increases from adding that example test case on a few, maybe 20 or so benchmarks. So there's obviously space to do better in terms of prompt engineering here. And this also applies to updated machine large language models other than Codex, right? There could be a lot more performance to be had there. Another thing I want to mention is that the evaluation I've really just focused on coverage increases, which is not necessarily related to bug finding ability. And if we want to find bugs with a test suite, we should probably have assertions in that test suite. And Codex generations do contain assertions, right? Like the ones that I mentioned earlier. This is the Codex generation I brought up earlier. There are some assertions there. Maybe we could use those. But actually in the example above, at least the first assertion is actually semantically incorrect. 0.0.0 should turn into 0.0.1, not 1.0.0. So there is some potential here for maybe using what Codex or another large language model is generating for better assertion generation, but it's not a slam dunk. And finally, another thing I just want to mention is that the Codex generating tests generally look a lot more natural than the ones generated by our search-based software testing tooling. It might be useful if we expect humans to ever look at these test suites to see whether we can preserve some of that naturalness while maintaining the advantages we get of mutative search. So on that note, I just want to close on kind of a higher level. So what we did in CodaMOSA is we exploited the synergy between large language models and mutational search, where large language models are really, really good at giving us what is most expected given the prompt. And mutational search is really, really good at giving us something that is close to what we started with, but unexpected. And in CodaMOSA, we exploited that synergy to improve the performance of search-based software testing, but there's a lot of other search problems out there in PLSE and further. And I think we can do a lot by exploiting the synergy between LLMs plus these tools we have that work really well, like say mutational search. So that is kind of the high-level summary slide. If you want to learn more, you can refer to our ICSE 2023 publication, CodaMOSA, Escaping Coverage Plateaus and Test Generation with Pre-trained Large Language Models. Thank you very much for listening.